In this video for Unit 2, Part 1, Lesson 4 of Calculus, I'm going to present to you the derivative rules that I would like for you to memorize before our quiz next week. There is a list of 34 derivative rules that I'd like to have you memorize. Actually, I'm going to modify that. Sorry, 28 rules that I want you to memorize. This group from here down you can put on a note card and bring to class. These are pretty often referenced rather than memorized. But in this entire list of derivative rules, these are the ones that are most common that we encounter when simplifying larger functions. Now, for every one of these rules, a proof has been completed in order to establish the rule, like we see over here on the right-hand side. Essentially, a mathematician had to sit down with our derivative definition, that limit definition of our difference quotient, and prove why the rule exists. So as you can see here on the screen, I use the difference quotient with the equation mx plus b, and I simplified that and ended up with a result. The derivative function of the linear function mx plus b is simply equal to m. Or in other words, the slope of a linear equation at any point is always this m value. Now, internally, we already knew that, but formally, it's nice to have a list of rules. And so here they are. Here's the first 5. The derivative of a constant number is always 0. The derivative of x is always 1. The derivative of negative x is always negative 1. The derivative of a linear equation, mx plus b, is always m. And the derivative of some constant times another function is the constant times the derivative of the function. Now here again, instead of taking the time to prove these rules, I'm happy to give them to you as long as you have them memorized for next week. We won't necessarily spend time proving why these are true. We'll just jump into using them in the applied context. Here are the next 5. Number 6 we call the sum or difference rule, where the derivative of a combination of functions that are being added or subtracted is simply the derivative of each added or subtracted together. 7 and 8 are both examples of the power rule. Number 7, if you have no leading coefficient. 8, if you do have a coefficient, it's just a reminder that the power multiplies by the number that's acting as our coefficient. Number 9 is an extension of the power rule as well, but it's pretty common for use with radicals. And number 10, also an extension of the power rule with negative exponents in a sense, but this shows us how to handle simple rational functions. Personally, I think it's a good idea to make flashcards for each one of these rules and start memorizing those immediately so that come Monday when we take our quiz, you'll be prepared for that. You'll have all of these memorized. Now in this next group of 5, we start getting into specific functions that do show up quite a lot in the real world, and therefore we're going to practice in calculus. The derivative of the exponential function with the natural base e is itself. The steepness or the slope of this function is always equal to the function value itself. That's an interesting concept and an interesting find that we'll discuss later. If there happens to be a different steepness to the growth curve or a growth rate k, we can modify the derivative with an outside multiplier or a constant multiplier k. If the base is anything other than the natural base e, well, we can account for that too by multiplying by the natural logarithm of that b times b to the x power. And then with 14 and beyond, we start getting into derivatives of trigonometric rules. The derivative of sine is cosine. The derivative of cosine is the opposite of sine. Again, we're going to see a lot of these in examples or in context later, but for right now, it's good to know what the rules are now so that you can focus on how they can be used when we get into them a little bit later. I'm going to run out of room here, so let's talk about 16 through 18 next. For the derivative of tangent, that's equal to secant squared of x. Remember, when we use the notation secant squared, that really means secant of x raised to the second power. Any trig function that contains a squared symbol before the argument x really means that trig function evaluated at x squared as a group. Convention, at least when written on paper, allows us to write this way as opposed to this way. Although interestingly, when we enter this expression into a calculator, most of the time we do have to write it like this one over here on the right. So an interesting find to keep in mind. For cosecant of x and secant of x, those two trig functions, their derivatives are as follows here. And now we'll slide on down to some others. With number 19, it's our final trig equation and its derivative. Each year I tell myself to reorder this, but I should have put rule number 19 closer to number 16 because tangent and cotangents derivatives look so similar. So if you'd like to reorder that, you're welcome to do so. For number 20, we call this the quotient rule, and 21 is what we call the product rule. And these are used quite frequently. There's a little phrase that goes with the quotient rule to help remember this, and it goes something like this: low d high minus high d low over low low. Again, that's low d high minus high d low over low low. And that phrase, the more you say it, the more you'll understand it, is saying the lower function g of x times the derivative of the higher function f of x. So we've got low function times the derivative of the high function minus the higher function times the derivative of the lower function. And high and low in this case literally means the upper and lower function on the fraction bar. All of that's divided by low low, or the low function squared. So one more time, that phrase low d high minus high d low over low low will help you keep the order of the quotient rule correct. And order does matter here because when we're subtracting and when we're dividing, those operations are not commutative. So you can't just switch the direction of subtraction or division. You got to get them in the correct order, and that phrase should help you do that. For the product rule, the order doesn't matter with regards to these two groups that are being summed together. But if you'll notice, the order of the product rule, as I have it written here, is the same as the numerator of our quotient rule. The grouping's the same. The difference, of course, is that we're using a subtraction symbol for our quotient rule numerator, and we're using an addition symbol for our product rule. So hopefully that'll help you keep those in mind. Again, as we switch to more specific functions, the natural log of x, a lot of times we'll restrict the domain of the function itself, and as long as we're dealing only with positive x values, that's what's being shown here with our absolute value function, then the derivative of the natural log is simply 1 over x. The only restriction here is that x is not allowed to be equal to 0 for obvious reasons. We can't have a 0 in the denominator. If we don't restrict the domain for our x values, then the derivative of the natural log of x is still 1 over x, but this rule only holds true when x values themselves are positive or bigger than 0. We can't substitute a negative number into a logarithm. And in this set, for the logarithm with a base other than 10 and other than e, we're going to take 1 divided by the natural log of the base value and multiply that times 1 over x. Here again, without the domain restriction in the equation, we are going to say that this is only true when x values are positive. We can't evaluate a logarithm with negative argument values. Number 25 is called the chain rule. And that's a pretty important one to remember. We use this one all the time when equations get complicated. So it would be worthwhile to research this one on your own, as well as the quotient and product rule. But in a sense, what we're saying is that if we've got a composition of functions where one function is the argument of another function, or is inside of another function, we would take the derivative of the outside function but leave the inside function alone for the time being. And then after that outer function's derivative is calculated with respect to the inner function, then we turn around and multiply by the derivative of the inner function. We'll see some examples of this later next week. For 26 through 28, these are all extensions of the chain rule in some specific example. E raised to the power of a function, so it's not just e to some number x, but e to an equation or a function f of x. Well, the derivative, similarly to the other power rule for the base e, is e to that power f of x. We account for the offset by multiplying by the derivative of the function f of x. And this again is our extension of the chain rule. For number 27, we have, well, what started off as 1 over f of x times the derivative f prime of x. But rather than showing a fraction times another function, we just combine those two when they multiply together, f prime divided by f. And this is, again, only possible if the function results for f are positive. We can't have an argument of a logarithm being a number that's less than or equal to 0. Lastly, for number 28, the derivative of some unknown base other than e or other than 10, well, no, this would work for 10 too, but other than e, natural log of b times b to the f of x power multiplied by the derivative of that inner function f prime of x. So certainly, as I introduce these rules now, they are going to be very foreign to you and unusual. But much like an elementary student has to learn the alphabet before they can start spelling words, it's helpful to learn these rules before we start using them. That way, we can focus on how to use those properly and in what context, rather than trying to learn the rules and see their application simultaneously. So memorizing these ahead of time will pay off in the long run. For numbers 29 through 34, as I said at the start of this video, go ahead and make a note card for these and bring them to class. Not only are they challenging because we're dealing with trigonometric functions, but they're also challenging because they're inverse trigonometric functions. And if I'm being perfectly honest, many of our derivative rules, even more so that are in this video, are known and they've been established, but they're not often memorized. And somebody that's working in this field would likely reference these derivatives in a chart or in a table off to the side. The first 28 or so, however, I think are good to be memorized because we'll use them so frequently that it's going to be faster to have them memorized. But this last group, it's fine to look them up. And in these inverse trigonometric function rules, there are domain restrictions for each. For example, in number 29 and 30, this rule on the left here, these rules are only good for x values that exist between -1 and +1 exclusive. We don't include those endpoints. And that's because the inverse of these trig functions only has a domain between -1 and +1 inclusive. We have to exclude the values 1 and -1 due to the division by 0. If x was ever equal to 1, well, now we've got a 0 in the denominator, which we can't have. For number 31 and 34, this notation looks a little bit strange. You may not have seen this before, but it would read, this upside down ace is for all. So we're saying for all x values that are an element of the real number set. So this is just a fancy way of saying that this derivative rule works for all real numbers. I thought I'd throw that in there just to share with you some notation that you may see in the future. Finally, for number 32 and 33, we're restricting our domain to be x values whose absolute value is greater than 1. And if you're thinking of a number line, x values whose absolute value is greater than 1, well, those would be numbers to the right of +1 and to the left of -1. So here we go, -1 to +1. The absolute value of these numbers here are greater than 1, and the absolute value of these numbers here are greater than 1 as well. So let me, maybe I'll try to color code this a little bit better. Let's try that again. For these two functions, the domains here exist to the right of 1, to the left of -1, whereas these two functions at the top, those exist only between -1 and +1. And then these functions down below for tangent and cotangent, well, the inverse functions there are or have a derivative formula that works for all real numbers. And hopefully if you are familiar enough with the graph of these inverse trig functions, or if you take a look at them, you'll understand why the domains for these are the way they are. So if you would, just make sure that you go back and rewind and replay parts of this video as you need it for their explanation, but more importantly, so that you can build your note cards from them and start memorizing them, because we will have a quiz first thing next week. Thanks for watching. Good luck.